Computer vision is one of the most powerful fields in artificial intelligence, teaching machines to see, interpret, and act on the world around them. From image classification to object detection, from 3D reconstruction to medical imaging, and from GANs to vision transformers, computer vision is transforming industries at lightning speed. In this guide, you'll explore 200 unique interview questions and answers, structured in an interview-style format that goes beyond memorization. Each answer is clear, practical, and designed to show you how to think and communicate like a true computer vision engineer. We'll cover the fundamentals: CNNs, detection, 3D vision, generation, applications, deployment, ethics, and future trends. Everything you need to stand out in interviews at Google, Microsoft, OpenAI, Meta, or any cutting-edge AI company. This is your complete computer vision interview prep blueprint. Let's begin. What is computer vision, and how does it differ from image processing? Computer vision is a field of AI that enables machines to interpret and understand visual information from the world images and videos. Unlike classical image processing, which focuses on low-level operations like filtering, resizing, or edge detection, computer vision combines these operations with machine learning and deep learning to extract higher-level meaning such as object detection, recognition, and scene understanding. In short, image processing transforms images, while computer vision interprets them. What are pixels, and why are they important in vision? A pixel is the smallest unit of a digital image, representing color intensity values in one or more channels. For grayscale, it's a single value. For color, it's typically RGB values. Pixels form the foundation of visual data, and all computer vision models operate by analyzing patterns in pixel values. Understanding pixels is key to building algorithms that detect shapes, textures, or objects. Explain the concept of image channels. RGB, grayscale. Image channels represent different components of color. A grayscale image has one channel, capturing brightness. An RGB image has three channels: red, green, and blue, which combine to form full-color visuals. Some tasks use alternative color spaces like HSV or YCBCR. Channels allow computer vision models to extract richer features than intensity. What is a histogram in images? An image histogram shows the distribution of pixel intensity values. For grayscale, it plots how many pixels fall at each brightness level. In color images, histograms can be built per channel. Histograms are used for tasks like contrast adjustment, thresholding, and image equalization, giving insights into an image's overall tone and quality. What is edge detection, and why is it important? Edge detection identifies boundaries where pixel intensity changes sharply, highlighting object outlines. It simplifies image data by focusing on structural features. Edges are crucial for tasks like object recognition, segmentation, and motion detection. Without edge detection, distinguishing shapes from raw pixel data would be much harder. How is thresholding used in image segmentation? Thresholding separates objects from the background by turning grayscale images into binary ones. Pixels above a threshold become white, others black. Simple global thresholding works in uniform lighting, while adaptive thresholding handles variable illumination. It's a fast, fundamental method for segmentation in applications like compare Sobel, Prewitt, and Canny edge detectors. Sobel and Prewitt are gradient-based operators that detect edges by measuring intensity changes in horizontal and vertical directions. Sobel is slightly better at noise suppression. Canny is more advanced. It applies smoothing, gradient calculation, non-maximum suppression, and hysteresis thresholding. Canny produces cleaner, thinner edges and is widely used in practice. What is morphological image processing? Morphological processing applies shape-based operations, often on binary images. Common techniques include erosion, shrinking objects, dilation, expanding, opening, erosion followed by dilation, and closing, dilation followed by erosion. These clean up noise, separate connected objects, and refined segmentation results in tasks like OCR and medical imaging. What is convolution in image processing? Convolution is applying a filter, kernel, over an image to compute weighted sums of neighboring pixels. It extracts features like edges, textures, or blurs. In computer vision, convolution forms the basis of CNNS, which automatically learn filters to capture patterns. From simple edges to complex objects, what is the Fourier transform in vision? The Fourier transform represents an image in terms of its frequency components rather than spatial pixels. Low frequencies capture smooth variations, while high frequencies capture edges and fine details. It's used in filtering, compression, and denoising. Many image processing techniques leverage Fourier transforms to analyze or modify images in the frequency domain. What is image filtering? Image filtering modifies pixel values based on neighbors, using kernels to enhance or suppress features. Smoothing filters reduce noise, while sharpening filters emphasize edges. Filtering underlies many vision tasks, from pre-processing before recognition to feature extraction in CNNs. Compare Gaussian blur versus median filtering. Gaussian blur smooths images using a weighted average where closer pixels matter more, reducing high-frequency noise but blurring edges. Median filtering replaces each pixel with the median of its neighborhood, preserving edges better while removing salt and pepper noise. Gaussian is best for general smoothing, while median excels at outlier noise removal. What is image normalization, and why is it needed? Image normalization scales pixel values to a consistent range, often 0 to 1 or -1 to 1. This ensures uniform input from models, preventing bias towards certain intensity ranges. Normalization speeds up convergence, improves stability, and is standard in training deep learning vision systems. Explain histogram equalization. Histogram equalization redistributes intensity values to enhance contrast. It spreads out frequent intensity ranges, making dark regions lighter and bright regions darker. This improves visibility in low-contrast images, like X-rays or poorly lit photos. Adaptive methods like CLAHE apply equalization locally to avoid overamplification. What are key points in computer vision? Key points are distinctive, repeatable points in an image, like corners or blobs that remain stable under transformations. They're used in matching, tracking, and reconstruction. Algorithms like SIFT and ORB detect key points, which form the basis of feature-based recognition and alignment tasks. What is feature matching in vision? Feature matching compares descriptors of key points across images to find correspondences. It's used in object recognition, stitching, and 3D reconstruction. Matching techniques include brute force search or approximate nearest neighbors. Robust matching ensures consistent alignment even under scale, rotation, or lighting changes. Compare SIFT, SURF, and ORB. SIFT detects scale invariant features, robust to rotation and illumination, but is computationally expensive. SURF speeds things up with approximations but is patented. ORB is a lightweight, free alternative combining FAST, key point detection, with BRIEF descriptors. ORB is fast for real-time tasks, while SIFT remains highly robust. What is optical flow in vision? Optical flow estimates pixel-level motion between consecutive video frames. It assumes brightness consistency and small motion. Dense optical flow computes motion for all pixels, while sparse flow tracks key points. Applications include video stabilization, motion detection, and action recognition. What is template matching? Template matching slides a small reference image over a larger image, comparing similarity at each location. It's useful for finding known patterns but struggles with scaling, rotation, or lighting changes. While simple, it works well in controlled environments. What is image registration? Image registration aligns two or more images into a common coordinate system. It's critical in medical imaging, satellite monitoring, and panorama stitching. Techniques rely on feature matching, intensity-based alignment, or geometric transformations like affine or homography. What is homography in computer vision? Homography is a transformation that maps points from one plane to another, preserving straight lines. It's widely used in stitching panoramas or projecting one view of a scene into another. Homography requires at least 4 corresponding points to estimate. What is perspective transformation? Perspective transformation warps an image to simulate viewing it from another angle. For example, correcting tilted document photos. It's a projective transform that accounts for depth perspective, unlike simple affine transforms. Used in augmented reality and 3D reconstruction. Explain Huff transform in line/shape detection. The Huff transform maps edge points into a parameter space to detect geometric shapes like lines or circles. For lines, points map to sinusoidal curves, and intersections reveal lines. It's robust to noise and partial occlusion, making it effective in tasks like lane detection. What is corner detection? Corner detection identifies points where intensity changes sharply in multiple directions, like intersections of edges. Harris corner detector and Shitomasi are classic methods. Corners are stable and distinctive, making them valuable for feature matching and tracking. What is motion detection in videos? Motion detection identifies changes in a sequence of frames. Simple methods include frame differencing, while advanced approaches use optical flow or background subtraction. Motion detection powers applications like surveillance, activity recognition, and autonomous driving. It's a foundation for higher-level video analysis. Why are CNNs widely used in vision tasks? Convolutional neural networks, CNNs, are designed to exploit the spatial structure of images. Instead of connecting every pixel to every neuron, CNNs use local receptive fields and shared weights, drastically reducing parameters while capturing patterns like edges, textures, and shapes. Stacking layers builds hierarchical features, making CNNs highly effective for classification, detection, and segmentation. Their efficiency and accuracy make them the backbone of computer vision. What is a convolutional filter? A convolutional filter, or kernel, is a small matrix of weights that slides over the input image to detect patterns. For example, one filter may detect vertical edges, another horizontal edges. Filters are learned during training, enabling CNNs to automatically discover the best features for the task, unlike handcrafted filters in classical vision. Explain receptive fields in CNNs for vision. The receptive field is the region of the input image that influences a particular neuron. In early layers, receptive fields are small and capture fine details like edges. In deeper layers, they expand to cover larger regions, detecting objects or shapes. Understanding receptive fields helps explain why CNNs can represent both local and global features. What is stride and padding in CNN-based vision tasks? Stride defines how far the filter moves after each step. A stride of 1 scans pixel by pixel, while higher strides downsample the feature map. Padding adds extra pixels, often zeros, around the image to control output size. Without padding, feature maps shrink after each layer. Together, stride and padding control spatial resolution in CNNs. Why is max pooling important in image analysis? Max pooling downsamples feature maps by selecting the maximum value in each region. It reduces spatial size, cuts computation, and makes features more invariant to small shifts. For example, if an edge shifts slightly in position, max pooling ensures it's still detected. Pooling is key to building robust vision systems. What are feature maps in CNNs? Feature maps are the outputs of convolutional filters applied to an image. Each map highlights where a specific feature, like an edge or corner, appears. Stacking feature maps across layers builds a hierarchy, low-level patterns in early layers and high-level structures in deeper ones. They're the internal representation that CNNs use to understand images. What is transfer learning in computer vision? Transfer learning reuses CNNs pre-trained on large datasets like ImageNet. Lower layers, which learn generic features like edges and textures, are kept, while higher layers are fine-tuned for the new task. This approach saves time, reduces the need for large datasets, and often improves accuracy in specialized domains like medical imaging or satellite analysis. How is fine-tuning applied in vision models? Fine-tuning involves loading a pre-trained CNN, freezing some layers, and retraining others on new data. Early layers, which capture generic features, are often frozen, while later layers adapt to task-specific features. Learning rates are usually smaller to avoid overwriting pre-trained knowledge. Fine-tuning is standard practice in applied computer vision. Compare AlexNet, VGG, and ResNet. AlexNet sparked the deep learning revolution in 2012 with 5 convolutional layers, ReLU activations, and dropout. VGGNet followed with very deep networks using only 3x3 filters, proving depth improves accuracy. ResNet introduced residual connections, solving vanishing gradients and enabling networks hundreds of layers deep. AlexNet was groundbreaking. VGG simple but heavy, and ResNet scalable and practical. What is EfficientNet in vision tasks? EfficientNet scales networks systematically by balancing depth, width, and resolution using a compound scaling method. Unlike arbitrary scaling, it finds an optimal trade-off. EfficientNet models achieve state-of-the-art accuracy with fewer parameters, making them ideal for applications needing both accuracy and efficiency, like mobile vision systems. What is MobileNet and why is it useful for vision? MobileNet is a lightweight CNN architecture optimized for mobile and embedded devices. It uses depth-wise separable convolutions to reduce computation and parameters significantly. While smaller than models like ResNet, MobileNet achieves competitive accuracy, making it a go-to choice for real-time applications on constrained hardware. What is InceptionNet? InceptionNet, introduced by Google, uses parallel convolutions of different sizes, 1x1, 3x3, 5x5 within the same layer to capture multi-scale features. It also employs 1x1 convolutions for dimensionality reduction, cutting computation. This architecture, popularized by GoogleNet, achieves strong accuracy with efficiency, influencing modern hybrid designs. What are dilated convolutions in vision? Dilated or Strauss convolutions expand the receptive field by inserting gaps between kernel elements. They capture multi-scale context without increasing parameters or reducing resolution. Dilated convolutions are widely used in semantic segmentation tasks like DeepLab, where both detail and context matter. What are depth-wise separable convolutions in vision? Depth-wise separable convolutions split convolution into 2 steps. Depth-wise, filtering each channel separately, and point-wise, combining with 1x1 convolutions. This drastically reduces computation and parameters. It's the key innovation behind MobileNet, enabling efficient deployment of CNNS on edge devices. What is global average pooling in CNNS for vision? Global average pooling, GAP, averages each feature map into a single value, replacing fully connected layers. GAP reduces parameters, prevents overfitting, and makes CNNS more interpretable. It's widely used in architectures like ResNet and Inception for classification tasks. Compare CNNS versus Vision Transformers, VITS. CNNS excel at capturing local patterns with strong inductive biases like translation invariance. Vision Transformers, VITs, use self-attention to capture global relationships directly. VITs often outperform CNNs on large datasets but require more data and compute. CNNs remain efficient and effective for smaller tasks, while VITs dominate at scale. What are Vision Transformers, VITS? VITs split images into patches, flatten them, and feed them into a transformer architecture originally designed for an LP. Self-attention models relationships between patches, enabling global context understanding. VITs eliminate convolutions, achieving strong performance in classification, detection, and segmentation when trained on large-scale datasets. What is the patch embedding process in VITS? Patch embedding divides an image into fixed-size patches, flattens them, and projects them into vectors using linear layers. These embeddings serve as tokens for the transformer. Positional encodings are added to preserve spatial order. Patch embedding is the foundation of how VITs process images. Compare ResNet versus VIT in vision tasks. ResNet relies on convolutions with residual connections, making it efficient and robust with moderate data. VITs use attention, excelling at capturing long-range dependencies. With small datasets, ResNet often performs better due to strong inductive biases. With massive datasets, VITs surpass ResNet in accuracy and flexibility. What is hybrid C and NVIT architecture? Hybrid models combine CNNS's local feature extraction with VITS's global context modeling. CNN layers handle early spatial patterns, while transformer layers capture long-range dependencies. This hybrid design improves performance on medium datasets where pure VITs might underperform. What is feature extraction from CNN layers? Feature extraction uses intermediate CNN outputs as representations for downstream tasks. Early layers capture edges and textures, while deeper layers capture objects. These features can power classifiers, clustering, or retrieval systems. Pre-trained CNN features are a strong baseline for many CV tasks. How are CNNs used for image classification? In classification, CNNs process images through convolution, pooling, and fully connected layers, or GAP. Each stage extracts progressively abstract features, and the final layer assigns class probabilities using softmax. CNNs excel at classification due to their ability to learn hierarchical visual patterns. What is multi-label classification in vision? Unlike single-label classification, multi-label classification allows images to belong to multiple classes simultaneously, such as dog and outdoor. Instead of softmax, sigmoid activation is used at the output to produce independent probabilities. It's common in tagging, medical imaging, or scene recognition. How do CNNs handle grayscale versus RGB images? For grayscale images, CNNs process a single input channel, while RGB images have 3 channels. Filters adapt accordingly. A grayscale filter may be 3 by 3 by 1, while an RGB filter is 3 by 3 by 3, 3 times 3 times 3. The architecture doesn't change fundamentally, but channel depth affects the filter design. What is domain adaptation in Vision CNNs? Domain adaptation tackles performance drops when a model trained on one domain, for example, daytime photos, is applied to another, for example, nighttime. Techniques include fine-tuning with target domain data, adversarial training, and domain invariant feature learning. Domain adaptation is critical for deploying CNNs in real-world, dynamic environments. What is object detection? Object detection is a computer vision task that identifies and localizes objects within an image. Unlike classification, which assigns a single label to an image, detection outputs both class labels and bounding boxes around objects. It's fundamental in applications like autonomous driving, surveillance, and retail analytics, where knowing what and where is equally important. Difference between image classification and object detection. Image classification predicts a single label or multiple labels for the entire image, while object detection identifies multiple objects and their positions using bounding boxes. For example, classification might say cat, while detection would say cat at top left, dog at bottom right. Detection is more complex as it requires spatial localization along with recognition. What is region proposal in object detection? Region proposals are candidate bounding boxes that may contain objects. Early detection methods like RCNN relied on generating thousands of proposals per image using algorithms like selective search. Each proposal is then classified by a CNN. Though accurate, proposal-based methods were slow, leading to faster approaches like YOLO and SSD. Explain RCNN. RCNN, regions with CNN features, generates region proposals using selective search, extracts CNN features for each, and classifies them with SVMs. While it pioneered deep learning in detection, it was slow due to repeated CNN computations for each region. RCNN set the foundation for faster end-to-end detectors. Explain fast RCNN. Fast RCNN improved on RCNN by running a CNN once on the entire image to produce a feature map, then applying region of interest, ROI, pooling for proposals. This reduced redundancy, making detection faster and more accurate. However, it still relied on external region proposal algorithms, limiting real-time use. Explain faster RCNN. Faster RCNN introduced a region proposal network, RPN, that generates proposals directly from CNN features, eliminating external proposal methods. This made detection nearly end-to-end and much faster. Faster RCNN remains a strong baseline for accuracy-focused detection tasks, though real-time performance is better with single-shot models. What is YOLO and why is it fast? YOLO, you only look once, treats detection as a single regression problem. predicting bounding boxes and class probabilities directly from the entire image in one pass. Unlike region proposal methods, YOLO doesn't scan multiple regions separately, making it extremely fast and suitable for real-time applications like robotics and self-driving. Compare YOLO versus SSD. Both YOLO and SSD are single-shot detectors. YOLO uses a grid-based approach, while SSD predicts boxes at multiple scales using feature pyramids. YOLO is faster with simpler design, while SSD provides better accuracy for smaller objects. In practice, both balance speed and accuracy, with YOLO often preferred for real-time use. What is ResNet? ResNet is a one-stage detector that introduced the focal loss function to address class imbalance between background and foreground objects. It achieved accuracy close to two-stage detectors like faster RCNN while maintaining speed. ResNet became a milestone in balancing precision and efficiency in detection. Explain anchor boxes in object detection. Anchor boxes are predefined bounding boxes of different sizes and aspect ratios placed across the image grid. Models like faster R, CNN, SSD, and YOLO predict offsets relative to these anchors. Anchors help detectors handle objects of varying scales and shapes, improving localization accuracy. What is non-maximum suppression NMS? NMS removes redundant bounding boxes that overlap heavily. It keeps the box with the highest confidence score and suppresses others with high intersection over union IOU. Without NMS, detectors might output multiple overlapping boxes for the same object. It's a key step in detection pipelines. What is intersection over union IOU? IOU measures the overlap between a predicted bounding box and the ground truth. It's calculated as the intersection area divided by the union area. IOU is used to evaluate detection accuracy, and in NMS to decide if boxes are duplicates. A typical IOU threshold for correct detection is 0.5. What are feature pyramids in detection? Feature pyramid networks, FPNS, exploit multi-scale feature maps from CNNS. Higher layers capture semantic richness but low resolution, while lower layers capture fine detail. FPNs merge both, enabling detectors to detect small and large objects effectively. They are a key innovation in modern detection architectures. Explain mask RCNN. Mask RCNN extends faster RCNN by adding a parallel branch to predict pixel-level masks for each detected object. This enables instance segmentation, distinguishing between multiple objects of the same class. It's widely used in medical imaging, autonomous driving, and robotics for precise object boundaries. What is semantic segmentation? Semantic segmentation assigns a class label to every pixel in an image. Unlike detection, which outputs bounding boxes, segmentation provides fine-grained understanding of scene structure. However, it doesn't distinguish between instances of the same class. All cars are labeled the same. What is instance segmentation? Instance segmentation is similar to semantic segmentation, but distinguishes between different instances of the same class. For example, two overlapping cars would be labeled as separate objects. Models like Mask RCNN achieve this by combining detection and segmentation. What is panoptic segmentation? Panoptic segmentation unifies semantic and instance segmentation. It labels every pixel while distinguishing individual object instances. For example, it would label road as background semantic and cars as separate instances. It provides a complete scene understanding, useful in robotics and autonomous driving. What is FCN, fully convolutional network? An FCN replaces fully connected layers with convolutional ones, allowing pixel-level predictions for segmentation tasks. It upsamples feature maps using deconvolution layers to match input resolution. FCNs mark the shift from patch-based segmentation to end-to-end deep learning methods. What is UNet? UNet is a CNN architecture for segmentation designed for biomedical images. It has an encoder-decoder structure with skip connections. The encoder captures context, while the decoder refines pixel-level predictions. Skip connections preserve details lost in downsampling, making UNet highly effective for medical and scientific tasks. What is DeepLab? DeepLab is a family of segmentation models that use dilated convolutions to capture multi-scale context. Later versions introduced atraspatial pyramid pooling, ASPP, and CRFS for refinement. DeepLab achieves state-of-the-art segmentation, especially for complex scenes like urban environments. Compare semantic versus instant segmentation. Semantic segmentation labels all pixels of the same class identically. All trees are one category. Instant segmentation goes further by distinguishing each tree as a separate object. Semantic gives class-level understanding, while instance provides object-level granularity. What is object tracking? Object tracking follows detected objects across video frames. It links detections over time, assigning consistent IDs. Tracking is essential for surveillance, autonomous driving, and sports analytics. Approaches include motion models, correlation filters, and deep learning-based trackers like Deep SORT. What is SORT tracking? Simple online and real-time tracking, SORT, combines object detection with Kalman filtering and Hungarian matching for tracking. It's fast and effective, but struggles with occlusions and re-identification. SORT is popular because of its simplicity and speed in real-time applications. What is Deep Sort? Deep Sort extends SORT by adding deep appearance features to re-identify objects after occlusion or misdetections. It improves tracking robustness in crowded or complex scenes. Deep Sort is widely used in surveillance and video analytics, where consistent tracking is critical. What is multi-object tracking? Multi-object tracking tracks multiple objects simultaneously across frames. It combines detection, association, and re-identification to maintain object identities over time. Challenges include occlusion, appearance changes, and clutter. Multi-object tracking is vital in traffic analysis, sports, and autonomous driving. What is 3D reconstruction in vision? 3D reconstruction is the process of creating a 3D model of an object or scene from 2D images or video. It uses geometric cues like multiple viewpoints, depth maps, or structure from motion to estimate 3D shape. Applications include AR and VR, robotics, cultural heritage preservation, and autonomous driving. It bridges the gap between flat images and real-world spatial understanding. What is stereo vision? Stereo vision mimics human binocular vision by capturing two slightly different viewpoints of a scene. By comparing disparities between left and right images, it estimates depth. Stereo vision is widely used in robotics, drones, and driver assistance systems to perceive distances and build 3D maps. What is depth estimation? Depth estimation predicts the distance of each pixel in a scene from the camera. It can be done via stereo vision, structure from motion, or deep learning using monocular images. Depth is crucial in AR/VR, autonomous navigation, and 3D scene understanding. What is structure from motion SFM? Structure from motion is a technique for reconstructing 3D structures by analyzing motion across multiple images taken from different viewpoints. By detecting and matching key points, it estimates both camera poses and 3D points. SFM underlies applications like 3D mapping, photogrammetry, and AR. What is SLAM simultaneous localization and mapping? SLAM enables a robot or device to build a map of an unknown environment while simultaneously tracking its own position. It combines visual, LiDAR, or sensor inputs with algorithms for feature matching and pose estimation. SLAM is central to robotics, drones, and autonomous vehicles for real-time navigation. What is monocular depth estimation? Monocular depth estimation infers depth from a single image using learned priors rather than stereo or LiDAR. Deep networks can predict relative depth by learning patterns like object size and perspective. Though less precise than stereo, it's valuable in mobile and low-cost applications. What is optical flow in video analysis? Optical flow estimates pixel-level motion between consecutive frames. It assumes brightness constancy and small movements. Dense optical flow provides motion for every pixel, while sparse flow tracks key points. Applications include video stabilization, action recognition, and motion prediction in autonomous driving. What is background subtraction in video? Background subtraction separates moving objects from a static scene. A background model is built, and deviations are marked as foreground. It's widely used in surveillance, traffic monitoring, and activity detection. Advanced methods handle dynamic backgrounds and lighting changes for robustness. What is background subtraction in video? Background subtraction separates moving objects from a static scene. What is action recognition in videos? Action recognition identifies human activities from video sequences, like walking, running, or waving. It combines spatial features from CNNS with temporal dynamics from RNNS, 3D CNNS, or transformers. Applications include sports analytics, video indexing, and smart surveillance. What is pose estimation? Pose estimation detects the positions of human joints and limbs in images or videos. 2D pose maps joints onto the image plane, while 3D pose reconstructs body orientation in space. It's used in AR, fitness apps, gaming, and motion analysis. OpenPose is a popular framework for this task. Compare 2D versus 3D pose estimation. 2D pose estimation locates joints in image coordinates, useful for gesture recognition and activity classification. 3D pose estimation reconstructs depth and orientation, enabling more realistic motion capture. While 2D is simpler and faster, 3D provides richer insights but requires more data and computation. What is gesture recognition? Gesture recognition interprets hand or body movements as input commands. It uses key point detection, motion tracking, and sometimes depth sensors. Applications range from AR and VR and gaming to human-computer interaction. It enables touchless interfaces and accessibility features. What is face detection? Face detection locates human faces in images or video streams. Early methods used HAR cascades, while modern methods use CNNS like MTCCN or retina face. Detection is the first step before recognition, emotion analysis, or face tracking in security and social media applications. What is face recognition? Face recognition identifies or verifies individuals by analyzing facial features. It maps faces into embeddings using models like FaceNet, then compares them via similarity metrics. Applications include security, identity verification, and smartphone unlocking. Privacy and fairness concerns are key challenges. What are facial landmarks in CV? Facial landmarks are key points like eyes, nose, and mouth corners detected on faces. They're used for alignment, expression analysis, and AR effects. Landmark detection ensures consistency across face recognition and is also used in medical and cosmetic analysis. What is emotion recognition? Emotion recognition classifies facial expressions into categories like happy, sad, angry, or surprised. It combines facial landmark detection, CNNS, and sometimes temporal modeling from video. Applications include mental health monitoring, customer feedback analysis, and entertainment. What is gait recognition? Gait recognition identifies individuals by their walking patterns. It uses silhouettes or pose estimation to extract unique features. Unlike face or fingerprint recognition, gait works at a distance and without cooperation, making it valuable in surveillance but raising privacy concerns. What is crowd analysis in video? Crowd analysis studies the behavior and movement of groups in video feeds. It estimates density, flow, or unusual activities. Applications include public safety, event management, and traffic monitoring. Challenges include occlusion and scale variations in dense crowds. What is video summarization? Video summarization condenses long videos into shorter versions while retaining key events. It uses scene detection, keyframe extraction, or deep learning to identify highlights. Applications include surveillance review, sports highlights, and media browsing. What is video object segmentation? Video object segmentation tracks and segments objects frame by frame. Unlike detection, it provides pixel-level boundaries. Techniques combine CNNS with temporal consistency, ensuring smooth segmentation across frames. It's crucial in video editing, AR, and robotics. What is video super resolution? Video super resolution enhances the resolution of video frames using deep learning. Models exploit both spatial details in frames and temporal redundancy across frames. Applications include surveillance, broadcasting, and medical imaging. It improves clarity in low-resolution footage. What is motion interpolation in video? Motion interpolation generates intermediate frames to create smoother video playback. It estimates optical flow or motion vectors to synthesize new frames. Applications include slow-motion video, animation, and frame rate conversion for displays. What is action localization? Action localization detects not just the type of action, but also where and when it occurs in a video. It outputs spatiotemporal boundaries, like bounding boxes across frames. This is critical in surveillance, sports analysis, and autonomous driving. What is temporal segmentation? Temporal segmentation divides a video into segments based on events or activities. For example, splitting a cooking video into preparation, cooking, and serving phases. Deep models identify transitions using features across frames. Temporal segmentation aids summarization, indexing, and video analytics. What is self-driving perception in video CV? Self-driving perception uses cameras and sensors to detect lanes, traffic signs, vehicles, and pedestrians in real time. It integrates detection, segmentation, tracking, and depth estimation. Perception is the foundation for decision-making in autonomous vehicles, ensuring safety and navigation. What is image generation in CV? Image generation is the process of creating synthetic images that look realistic, either from random noise, text descriptions, or other images. Deep learning models like GANs, VAES, and diffusion models power this field. Applications include data augmentation, art generation, product design, and medical imaging. The goal is to produce high-quality, diverse, and controllable outputs. How are GANs used in image generation? Generative adversarial networks, GANs, use a generator to create synthetic images and a discriminator to distinguish real from fake. Through adversarial training, the generator improves until its outputs resemble real images. GANs are widely used for photorealistic face generation, style transfer, and super resolution. What is conditional GAN in image generation? Conditional GANs extend GANs by conditioning both the generator and discriminator on additional information like labels or text. This allows controlled generation, for example, creating images of digits 0 to 9 or generating a cat versus a dog image on demand. Conditional GANs power applications like text-to-image synthesis. What is StyleGAN? StyleGAN, developed by NVIDIA, introduced a style-based generator that separates high-level attributes like pose from fine details like hair texture. This enables fine-grained control over generated images. StyleGAN produces photorealistic human faces and is widely used in synthetic media, dataset creation, and art. What is StyleGAN? StyleGAN enables unpaired image-to-image translation, such as converting horses to zebras or summer landscapes to winter ones without paired datasets. It uses cycle consistency loss to ensure translations can be reversed. StyleGAN opened the door to domain adaptation and artistic style transfer with unaligned data. What is Pix2Pix? Pix2Pix performs paired image-to-image translation. Given aligned input-output pairs, it learns mappings like sketches to photos or segmentation maps to images. Unlike StyleGAN, it requires paired data. Pix2Pix is widely used in tasks where input-output relationships are known, like satellite-to-map translation. What are diffusion models in CV? Diffusion models generate images by starting with random noise and iteratively denoising it through learned steps. They model the reverse of a gradual noising process. Diffusion models like Stable Diffusion and DALL-E 2 now achieve state-of-the-art results in text-to-image generation, surpassing GANs in quality and diversity. Compare GANs versus diffusion models in vision. GANs generate sharp, high-quality images quickly, but often suffer from mode collapse and unstable training. Diffusion models are slower, but produce more diverse and consistent results, excelling at high fidelity and controllable generation. Today, diffusion dominates creative applications, while GANs are still used where speed matters. What is image-to-image translation? Image-to-image translation converts images from one domain to another, like turning sketches into photos or day into night. Models like Pix2Pix and StyleGAN handle paired and unpaired cases. It's widely used in AR style transfer in domain adaptation tasks. What is text-to-image generation? Text-to-image generation creates images directly from natural language descriptions. Models like DALL-E, Stable Diffusion, and Midjourney use large-scale vision language pre-training and diffusion to map text prompts into realistic visuals. This enables artists, designers, and researchers to generate content directly from ideas. What is super resolution in vision? Super resolution enhances image resolution by predicting high-frequency details missing from low-resolution inputs. Deep models like SR-CNN and ESR-GAN achieve photorealistic results. Applications include medical imaging, satellite imagery, and restoring old photos. It's a key enhancement tool in vision. What is ESR-GAN? Enhanced Super Resolution. GAN, ESR-GAN, is a GAN-based model that improves over traditional super resolution by producing sharper, more realistic textures. Unlike older methods, ESR-GAN balances perceptual quality with fidelity, making it widely used in image restoration and enhancement tasks. What is image denoising? Image denoising removes noise from corrupted images while preserving important details. Traditional methods use filters, while deep models learn noise patterns directly. Applications include improving low-light photography, medical scans, and surveillance footage. Denoising is often combined with super resolution. What is image inpainting? Image inpainting fills missing or corrupted parts of an image with plausible content. Deep learning-based inpainting uses context to generate natural-looking fills, restoring old photos or removing unwanted objects. GANs and diffusion models power modern inpainting systems. What is deepfake generation? Deepfakes use GANs, or autoencoders, to replace faces or mimic voices in videos. While they enable creative applications like film production, they also raise serious ethical concerns about misinformation and privacy. Detecting and regulating deepfakes is an active area of research. What is neural style transfer? Neural style transfer blends the content of one image with the style of another by optimizing a CNN to minimize content loss and style loss. For example, turning a photo into a Van Gogh-style painting. It's a creative use of CNNs for art and design. What are autoencoders in CV? Autoencoders are neural networks that compress images into latent representations and reconstruct them. They're used for denoising, dimensionality reduction, and anomaly detection. In vision, autoencoders also serve as building blocks for generative models like VAES. What are VAES for image generation? Variational autoencoders, VAES, extend autoencoders by learning a probabilistic latent space. This allows sampling new images by drawing from the latent distribution. While outputs are often blurrier than GANs, VAES provides smooth, interpretable, latent spaces for controlled generation. What is latent diffusion for CV? Latent diffusion models operate in a compressed latent space instead of pixel space. This makes generation faster and more efficient while preserving detail. Stable diffusion is a prime example, combining autoencoders with diffusion in latent space to generate high-quality images from text or other inputs. What is face aging synthesis? Face aging synthesis predicts how a person's face changes over time. GAN-based models generate realistic aged or rejuvenated faces while preserving identity. Applications include forensics, missing person investigations, and entertainment. What is cartoonization in CV? Cartoonization converts real photos into cartoon-like images. It uses style transfer, GANs, or specialized filters to simplify textures and exaggerate edges. Popular in entertainment and AR apps, cartoonization is a fun but technically challenging task due to varying styles. What is photorealistic image synthesis? Photorealistic synthesis aims to generate images indistinguishable from real photos. Models like StyleGAN and diffusion networks push the limits of realism. This is used in game design, film production, and creating synthetic training data for AI systems. What is adversarial image generation? Adversarial image generation uses GANs or similar methods to create challenging examples that can fool vision models. While often used to attack models, It also reveals weaknesses and helps improve robustness by training models with adversarial samples. What is dataset augmentation via GANs? GANs can generate synthetic samples to expand datasets, especially when labeled data is scarce. For example, generating medical scans of rare diseases. Augmentation via GANs improves generalization, reduces overfitting, and balances imbalanced datasets. What is multimodal image generation? Multimodal generation combines multiple inputs like text, audio, or other images to generate visuals. For instance, generating an image from both a text description and a sketch. Multimodal models like clip plus diffusion are driving cross-modal creativity in AI. What is medical imaging in CV? Medical imaging in computer vision applies AI to interpret X-rays, MRIs, CT scans, and ultrasounds. Models detect anomalies, segment organs, and assist diagnosis. For example, CNNs can identify pneumonia in chest X-rays. Accuracy, interpretability, and regulatory compliance are crucial since errors can directly impact patient health. What is tumor detection in medical imaging? Tumor detection uses CV models to locate and classify tumors in scans. Techniques include segmentation with UNet or classification using CNNs. Challenges involve variability in tumor shape, size, and imaging quality. Reliable tumor detection accelerates diagnosis and supports doctors, but must always complement, not replace, clinical judgment. What is anomaly detection in radiology? Anomaly detection flags unusual patterns in medical images that deviate from normal anatomy. Autoencoders and generative models are often used. Poor reconstructions hint at anomalies. This approach helps spot rare conditions, though ensuring low false negatives is critical in healthcare. What is image analysis in pathology? In digital pathology, CV models analyze microscope images of tissue samples. Tasks include cell counting, tumor grading, and biomarker detection. High-resolution images make deep learning essential. Pathology CV supports faster, more objective analysis, though interpretability and integration with lab workflows remain challenges. What is computer vision in agriculture? Computer vision helps monitor crops, detect diseases, and estimate yields. Drones with CV models analyze fields, while image-based systems classify healthy versus diseased plants. Agriculture CV improves efficiency, reduces pesticide use, and supports sustainable farming by giving farmers real-time insights. What is crop disease detection? Crop disease detection uses CV to identify signs of infections on leaves or stems. Models trained on labeled disease images can detect early symptoms invisible to the human eye. This helps farmers take timely action, boosting yield and reducing losses. What is drone-based CV? Drone-based CV combines aerial imagery with AI for tasks like crop monitoring, disaster assessment, or construction inspection. Drones capture wide-area images, and vision models analyze them for insights such as vegetation health or infrastructure damage. This enables large-scale monitoring at low cost. What is satellite image analysis? Satellite CV processes Earth observation data for applications like land use classification, deforestation monitoring, and disaster response. Models handle huge images, detecting patterns invisible to humans. It's widely used in climate science, urban planning, and defense. What is land use classification? Land use classification categorizes areas in satellite or aerial images into classes like urban, forest, or water. CNNs and segmentation models identify regions based on texture and spectral information. Governments and researchers use it for planning, environmental monitoring, and agriculture. What is facial recognition security? Facial recognition security verifies identity by comparing detected faces with stored templates. It's used in access control, smartphones, and surveillance. While accurate, issues like bias, spoofing, and privacy concerns require safeguards like liveness detection and fairness audits. What is emotion detection in CV? Emotion detection interprets facial expressions or body cues to classify emotions like happiness or anger. CNNs and RNNs process features over time. Applications include customer feedback, education, and healthcare. However, cultural differences and privacy concerns limit widespread adoption. What is surveillance analytics? Surveillance analytics uses CV for tasks like motion detection, person tracking, and anomaly detection in video feeds. It helps in security, traffic monitoring, and crowd management. Ethical use is critical, as misuse can infringe on privacy and civil liberties. What is license plate recognition? License plate recognition, LPR, detects and reads vehicle plates from images or video. It combines detection, finding the plate region, with OCR, reading characters. LPR is widely used in traffic enforcement, tolling, and parking management. Challenges include varying lighting, angles, and plate designs. What is OCR, optical character recognition? OCR extracts text from scanned documents, photos, or videos. In CV, deep learning models detect text regions and recognize characters. OCR enables digitization of books, license plates, receipts, and more. Modern OCR handles multiple fonts, languages, and noisy inputs with high accuracy. What is scene understanding? Scene understanding goes beyond detecting objects to analyze their relationships and context. For example, identifying a person riding a bike on a street. It combines detection, segmentation, and reasoning. Scene understanding is key for autonomous driving and intelligent assistance. What is product recognition in retail? Product recognition identifies items from shelf images or checkout cameras. Models detect and classify packaging variations, barcodes, or logos. This powers cashierless stores, inventory management, and personalized shopping experiences. What is gesture-based interaction? Gesture-based interaction uses CV to interpret hand or body movements as input commands. Examples include waving to switch slides or pinching to zoom in AR. It enables touchless interfaces in gaming, presentations, and smart devices, improving accessibility. What is AR, augmented reality, in CV? Augmented reality overlays digital objects onto the physical world using CV for real-time tracking and alignment. AR apps detect surfaces, recognize objects, and adjust overlays dynamically. CV ensures virtual elements appear naturally integrated into the environment. What is VR, virtual reality, in CV? Virtual reality immerses users in a fully artificial environment. CV supports VR by enabling body tracking, gesture recognition, and realistic rendering. CV also ensures spatial alignment between the physical and virtual world, critical for immersion and interaction. What is mixed reality in CV? Mixed reality blends real and virtual worlds, so digital objects interact with physical ones in real time. CV detects surfaces, depth, and user actions to anchor objects realistically. MMR powers advanced AR and VR experiences in gaming, design, and training. What is autonomous driving perception? Perception in self-driving cars uses cameras, LiDAR, and radar to detect objects, lanes, and pedestrians. CV models perform detection, segmentation, and tracking in real time. Reliable perception is the backbone of decision-making and safety in autonomous vehicles. What is pedestrian detection in CV? Pedestrian detection locates people in images or videos, often in real time for driver assistance systems. CNN-based detectors like YOLO or FasterR, CNN, are used. Challenges include occlusion, varying poses, and crowded scenes. What is traffic sign recognition? Traffic sign recognition identifies road signs from camera feeds, classifying them into categories like stop, speed limit, or yield. It's crucial for ADAS and autonomous driving. CNNs handle recognition, while detection models localize signs in real time. What is lane detection in CV? Lane detection identifies road lane markings using edge detection, who transforms, or CNNs. It supports lane keeping and autonomous driving. Modern models use segmentation approaches for robust detection under varying conditions, like rain or faded paint. What is collision avoidance in CV? Collision avoidance systems use CV to detect obstacles and predict potential collisions. They integrate detection, tracking, and depth estimation to issue alerts or trigger braking. These systems are vital in autonomous vehicles, drones, and robotics for safe navigation. What is model compression in CV? Model compression reduces the size and complexity of computer vision models to make them faster and more efficient for deployment. Techniques include pruning, quantization, distillation, and low-rank factorization. Compressed models are critical for mobile, embedded, and real-time applications where compute and memory are limited. What is pruning in CNN-based vision models? Pruning removes unnecessary weights, neurons, or filters from a CNN. Unstructured pruning drops individual connections, while structured pruning removes entire channels or layers. This shrinks model size and speeds inference with minimal accuracy loss, making models more efficient for edge devices. What is quantization in CV models? Quantization reduces the precision of model weights and activations, such as from 32-bit floating point to 8-bit integers. This cuts memory usage and speeds computation, often with little accuracy drop. Quantization is standard in deploying vision models on mobile and embedded hardware. What is distillation for vision? Knowledge distillation transfers knowledge from a large teacher model to a smaller student model. The student learns not only from hard labels, but also from the teacher's soft outputs. In vision, distillation enables compact models that achieve near-teacher accuracy while being faster and lighter for deployment. What is edge deployment in CV? Edge deployment runs vision models directly on devices like phones, cameras, or IoT sensors. It reduces latency, preserves privacy, and avoids dependence on cloud servers. Techniques like pruning, quantization, and lightweight architectures, e.g. MobileNet, make edge deployment practical. What is real-time inference in CV? Real-time inference means processing images or video fast enough to respond immediately, typically under 30 milliseconds per frame. It's essential for applications like autonomous driving, AR/VR, and surveillance. Achieving real-time requires efficient models, optimized hardware, and parallelization. What is mobile CV optimization? Mobile optimization tailors vision models for smartphones, balancing accuracy and efficiency. It involves lightweight architectures, like MobileNet or EfficientNet Lite, quantization, and on-device accelerators like GPUs or NPUs. Optimized mobile CV powers applications like face unlock and AR filters. What is ONNX in CV? ONNX, Open Neural Network Exchange, is an open standard format for representing machine learning models. It allows models trained in one framework, example is PyTorch, to be deployed in another, example are TensorFlow or Caffe. In CV, ONNX ensures portability and accelerates deployment across platforms. What is TensorRT in CV? TensorRT is NVIDIA's SDK for optimizing and deploying deep learning models on GPUs. It applies optimizations like layer fusion, precision calibration, and kernel auto-tuning. For computer vision, TensorRT accelerates inference dramatically, making it a go-to tool for real-time CV deployment on NVIDIA hardware. What is OpenCV DNN module? The OpenCV DNN module allows running deep learning models within the OpenCV framework. It supports models from TensorFlow, PyTorch, and Caffe. This makes it easy to integrate trained models with classical vision pipelines for deployment in real-time applications. What is efficient video inference? Efficient video inference reduces redundant computation by leveraging temporal coherence between frames. Instead of processing every frame fully, models reuse features from previous frames or sample keyframes. This approach is critical for scaling CV systems to real-time video analytics. What is frame sampling in video CV? Frame sampling selects subsets of frames from a video for processing, reducing computational load. For example, analyzing every fifth frame instead of all frames. While this speeds up inference, it risks missing fast events, so adaptive sampling methods are often used. What is batch inference in CV? Batch inference processes multiple images simultaneously in one forward pass. It maximizes GPU utilization and reduces latency per image in high-throughput systems. While great for offline tasks, batch inference isn't always feasible for real-time applications that require per-frame predictions. What is model serving for CV applications? Model serving provides trained CV models as scalable APIs for production use. Tools like TensorFlow serving, TorchServe, or Fast API enable deployment with load balancing, monitoring, and versioning. Model serving is key to moving from research to real-world CV systems. What is latency optimization in CV inference? Latency optimization reduces the time between input and prediction. Techniques include quantization, pruning, parallel computation, and hardware acceleration, like GPUs, TPUs. For CV, where speed is critical, e.g., autonomous driving, latency optimization can be as important as accuracy. What is FPGA deployment in CV? FPGAs, Field Programmable Gate Arrays, provide customizable hardware acceleration for CV models. They balance efficiency and flexibility, consuming less power than GPUs. FPGAs are common in embedded vision applications, though programming them requires specialized expertise. What is cloud-based CV deployment? Cloud deployment hosts vision models on platforms like AWS, GCP, or Azure, providing scalability and compute power. Applications include video analytics, image search, and medical diagnostics. The trade-off is network latency and privacy concerns compared to edge deployment. What is TinyML for CV? TinyML deploys machine learning models, including vision, on ultra-low power microcontrollers. CV tasks like gesture recognition or simple object detection can run directly on devices consuming milliwatts. TinyML is key for IoT, wearables, and battery-powered devices. What is quantization-aware training? Quantization-aware training simulates lower precision operations during training, preparing models for post-training quantization. This helps maintain accuracy while enabling deployment on 8-bit hardware. In CV, it ensures models remain robust even after aggressive compression. What is neural architecture search in CV? Neural architecture search, NAS, automates the design of vision models. It explores combinations of layers, filters, and connections to discover efficient architectures. NAS produced models like EfficientNet, balancing accuracy and efficiency better than manual designs. What is automated augmentation in CV? Automated augmentation uses algorithms to discover the best data, augmentation policies for a dataset. For CV, this means learning transformations like rotation, color jitter, or cutout that improve generalization. Examples include AutoAugment and RandAugment. What is lightweight CNN design? Example are ShuffleNet, SqueezeNet. Lightweight CNNs like ShuffleNet and SqueezeNet are designed for efficiency on constrained hardware. ShuffleNet uses channel shuffling to reduce computation, while SqueezeNet achieves AlexNet-level accuracy with 50 times fewer parameters. These architectures enable real-time CV on mobile and embedded devices. What is MobileNet v3? MobileNet v3 combines depth-wise separable convolutions with squeeze and excitation modules and NAS-based optimization. It balances accuracy and efficiency better than previous MobileNets, making it ideal for tasks like face detection, object recognition, and mobile AR. What is Edge TPU for CV? Edge TPU is Google's specialized hardware accelerator for running TensorFlow light models efficiently on edge devices. It's optimized for CNN-based CV tasks, offering high throughput at low power. Edge TPU powers smart cameras, IoT, and on-device inference. What is batch normalization in CV deployment? Batch normalization normalizes activations during training, improving convergence and stability. For deployment, batch norm layers are often fused with convolution layers for efficiency. This reduces computation and ensures consistent performance across environments. Why is interpretability important in CV? Interpretability ensures we understand why a computer vision model made a certain prediction. In fields like healthcare or autonomous driving, a wrong decision can have serious consequences. Transparent explanations help build trust, debug errors, and meet regulatory requirements. Without interpretability, even highly accurate models may not be adopted in critical industries. What is GradCam in CV? GradCam, Gradient Weighted Class Activation Mapping, highlights image regions most responsible for a CNN's prediction. It uses gradients flowing into the last convolutional layer to produce heat maps. For example, in medical imaging, GradCam can show which part of an X-ray influenced the diagnosis, making AI decisions more transparent. What is occlusion sensitivity analysis? Occlusion sensitivity tests model interpretability by masking parts of an image and observing prediction changes. If blocking a region drastically reduces confidence, that area is important for classification. It's a simple but powerful way to visualize what features a CV model relies on. What is fairness in computer vision? Fairness in CV means ensuring models perform equally well across demographics, environments, and conditions. For example, face recognition systems should work reliably regardless of race, age, or gender. Biases often arise from unbalanced datasets, and addressing them is essential to avoid harmful or discriminatory outcomes. What is bias in face recognition systems? Bias occurs when face recognition systems show unequal accuracy across groups. For example, models trained on datasets skewed toward lighter skin tones may misclassify darker-skinned individuals. This can lead to unfair or harmful outcomes, highlighting the need for diverse datasets and fairness audits in deployment. What is adversarial attack in CV? An adversarial attack adds carefully crafted noise to an image that appears invisible to humans, but fools a CV model. For example, a stop sign altered slightly may be misclassified as a speed limit sign. These attacks expose vulnerabilities in vision systems, especially in safety-critical domains. What are adversarial patches in vision? Adversarial patches are visible patterns designed to fool CV models. Unlike subtle noise, these patches can be printed and placed in the real world. For example, a sticker that causes misclassification. They demonstrate the risks of physical adversarial attacks in security-sensitive CV systems. How to defend against adversarial attacks in CV. Defenses include adversarial training, where models are trained on perturbed examples, input preprocessing like denoising, and certified defenses that guarantee robustness within certain bounds. No defense is foolproof, so multiple layers of protection and continuous testing are necessary for real-world deployment. What is explainability in medical CV systems? Explainability in medical CV ensures doctors can understand and validate AI-driven diagnoses. Tools like GradCam highlight regions of concern in scans. Transparent models help clinicians trust AI assistance and comply with strict healthcare regulations. Black box predictions without explanations are often unacceptable in medicine. What are privacy risks in surveillance CV? Surveillance CV can capture and store personal data without consent, raising privacy concerns. Facial recognition in public spaces may enable mass tracking. Risks include misuse by authorities or hackers. Ethical CV deployment requires strong safeguards, transparency, and compliance with privacy laws like GDPR. What is ethical use of face recognition? Ethical use means deploying face recognition responsibly with user consent, fairness testing, and safeguards against misuse. Acceptable uses include device unlocking or voluntary ID verification, while mass surveillance or discriminatory profiling crosses ethical lines. Clear regulations and audits are essential for responsible adoption. What is green AI in CV models? Green AI focuses on reducing the energy and carbon footprint of training and deploying vision models. CV systems can be resource-heavy, especially large CNNs or transformers. Techniques like model compression, efficient architectures, and hardware optimization make CV more sustainable, balancing accuracy with environmental impact. What is robust CV under noisy conditions? Robust CV ensures models perform well despite noise, blur, lighting changes, or weather effects. Robustness is critical for real-world systems like autonomous driving. Techniques include data augmentation, adversarial training, and domain adaptation. Robustness testing is part of safe deployment. What is domain adaptation in CV? Domain adaptation helps CV models trained in one environment perform well in another. For example, adapting a daytime train detector for nighttime use. Techniques include fine-tuning with target domain data, adversarial training, or style transfer. Domain adaptation is key to real-world generalization. What is zero-shot vision? Zero-shot vision solves tasks without direct training examples, often by leveraging pre-trained vision language models like CLIP. For instance, a model trained on image-text pairs can classify new categories by interpreting text prompts. Zero-shot methods reduce reliance on labeled datasets and improve flexibility. What is few-shot learning in CV? Few-shot learning enables CV models to learn new categories from just a handful of labeled examples. Techniques include meta-learning, prototypical networks, and transfer learning. Few-shot learning is valuable in specialized domains like medical imaging, where collecting large data sets is difficult. What is self-supervised learning in vision? Self-supervised learning creates supervisory signals from unlabeled images, such as predicting missing patches, rotations, or contrastive relationships. Models like SIM-CLR and MoCO pre-train powerful visual representations that can be fine-tuned with small labeled datasets. Self-supervision reduces dependence on costly annotations. What are multimodal vision models? Example is CLIP. Multimodal models like CLIP learn joint embeddings of images and text by training on large image caption datasets. This enables zero-shot classification, retrieval, and cross-modal tasks. Multimodal vision is transforming AI by bridging visual and linguistic understanding, powering applications like text-to-image generation. What is vision language pre-training? Vision language pre-training aligns visual and textual data in a shared space using transformers. Tasks include image captioning, visual question answering, and cross-modal search. Pre-trained models like CLIP and BLIP demonstrate how combining modalities enhances flexibility and generalization. What are embodied AI and vision? Embodied AI combines CV with robotics, enabling agents to perceive and interact with the physical world. For example, a robot using vision to navigate, grasp objects, or learn tasks. Embodied vision integrates perception with action, paving the way for intelligent robots and assistants. What is neurosymbolic vision? Neurosymbolic vision combines deep learning's pattern recognition with symbolic reasoning for logic and rules. It enhances explainability and reasoning, such as understanding object relationships in a scene. This hybrid approach aims to overcome deep learning's black box limitations. What is 3D multimodal vision? 3D multimodal vision integrates 3D data, like point clouds, with images, text, or audio. It enables richer scene understanding, critical for robotics, AR and VR, and autonomous vehicles. For example, combining 3D LiDAR with images improves depth perception and object recognition. What is future of AR and VR in CV? The future of AR and VR in CV lies in seamless integration of virtual and physical worlds. Advances include real-time 3D reconstruction, gaze tracking, and multimodal interaction. CV ensures immersive, responsive experiences for gaming, education, and remote collaboration. What is foundation model for CV? A foundation model is a large pre-trained CV model designed for general-purpose use across tasks. Examples include vision transformers trained on billions of images. Once pre-trained, they can be fine-tuned for specific tasks with minimal data. Foundation models are reshaping CV by providing scalable, flexible starting points. What is the future of computer vision research? The future of CV will focus on multimodal integration, foundation models, and efficient architectures for real-world deployment. Research is moving toward robust, interpretable, and fair systems that work reliably across domains. Applications in healthcare, AR and VR, robotics, and autonomous driving will expand rapidly, with CV becoming an invisible backbone of everyday technology. You've now covered 200 computer vision interview questions and answers, spanning fundamentals, deep learning architectures, real-world applications, and the future of vision. But remember, interviews are not just about recalling facts. They're about explaining concepts, solving problems, and showing how you apply computer vision in practice. Keep revisiting these questions, practice answering them out loud, and connect each idea to real-world examples. The more you refine your answers, the more confident you'll become. Computer vision is moving fast, powering autonomous vehicles, AR and VR, medical diagnostics, and multimodal AI. By mastering these concepts, you're not just preparing for interviews, you're preparing for the future. If this helped you, share it, practice with peers, and subscribe for the next big series on NLP, reinforcement learning, recommendation systems, and generative AI. The journey continues, and your next opportunity is waiting.